Sit down, sit down, sit down. Let's start. We have a little bit that have to cover. The most important thing. Okay, now I would like to present to you the unified model. Unified model for annular flow. Okay. You may wonder, hey, what about our transition J? Transition J works for vertical pipe, okay, vertical flow, upward vertical flow. And in the horizontal flow, we use transition B, right? In the exam flow, I asked about, okay, what is the equation number for transition J and what is the page number? What is the transition for equation for transition B and what is the page number? So you should quickly know the answer. I am very positive that kind of question is in the exam. Okay. Transition J is for upward vertical flow. Now, by 1986, try to make it to work with any angle. Okay. Transition A from Title Douglas is good already. So transition A, but in 1986 tell us that it works for any angle. Okay, transition A, criterion for transition A work for any angle. Okay, transition A, stratified to non-stratified, it works for any angle. But for different kind of angle, it may end at different location. But that transition A works at any angle. So they try to develop transition J that works for any angle too. So what they do is they start with the combined momentum equation. Okay, look at this. That is a combined momentum equation. But this time, assume no entrainment. The reason I strongly believe that the reason that they assume no entrainment because at the transition between annular flow to slug flow, we really not have entrainment, or we can neglect entrainment, right? Let's think about annular flow. Annular flow has droplet in the middle, right? When we about to, let's say we decrease the gas flow rate. When gas flow rate go down, we are about to change to another flow pattern. At the point that we change, we may not have much force from gas to make a droplet, to create droplet in the core. So to simplify everything, assume no entrainment. So this is not to get pressure drop, but to get the transition. Okay, right. So this is a combined momentum equation. Is this the same or different than what we have seen earlier? Look at your textbook. Okay, look at your textbook. Everyone, that's why I asked you to bring the book. Sweta, can you look at page 160, equation 4.81? Are they the same? Are they the same? 160, 4.81. Vega, are they the same? Which term is not the same? Okay, that's the only difference, right? They change from C to G, just that. AC to AG, rho C to rho G. The rest, the same. So that is because we assume no entrainment. So that's a combined momentum equation for no entrainment. Okay. Yes? Question? No question? Okay, let's move on. So once we have the combined momentum equation, this is combined momentum equation, right? It works for any angle, correct? Given that we have that kind of flow, we have film, we have gas core, so that combined momentum equation is work. If we have non-uniform film, that combined momentum equation will give us error. Okay, but it kind of works, but it will have more error if the film is not uniform. If the film at the bottom is thicker than the film at the top, this combined momentum equation is not perfectly valid. This is based on the assumption that it's uniformly distributed. Okay. Once we have combined momentum equation, so you see this tau I, interfacial shear stress. So early on, tau I is multiplied by SI ALAG, right? SI ALAG is dependent upon thickness, film thickness. Substitute all those things, we get tau I divided by something as a function of film thickness, and tau WL divided by something as a function of film thickness. Okay, rearrange it. We get this equation 5.19. Where's the page number for 5.19, Hakim? 5.19, of course, it is in chapter 5. June, where's 5.19? Page what? 100, 201. Okay. So that equation 5.19 is a combined momentum equation. Okay, it's come from combined momentum equation when we assume no entrainment for annular flow. Okay, that is 5.19. When we look at it, we can rearrange and express it as a shear stress, interfacial shear stress tau I. Tau I equal to blah 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 blah. All those things. The left hand side, the key here is the left hand side is the required interfacial shear stress. That allow us to get the film thickness of delta L. Okay, this means if we have a certain film thickness, we require a certain shear stress to keep it that thick, right? Gas core moving up. So when gas core moving up, we have some thickness. Okay, we have some thickness of the film. So there's a relationship between the required shear stress and the film thickness. So let's look at the solution of this thing. You have this graph, right? Let's look at the solution. Okay, look at this one. Solid line is 5.19. You see solid line, okay, let's say this solid line, right? That's solid line, that is solid line. We plot it between dimensionless interfacial shear stress and thickness. See that thickness, that shear stress. This graph tell me that, okay, let's pick one line. Okay, let me pick this line. So when I pick this line, this tell me, hey, if I want a thin film, like this film, I have to have a lot of gas flow rate or a lot of shear stress so that we can have thin film. So tau I is calculated from half Fi rho v sub g squared, right? That is tau I. Okay, that is tau I. So this means if gas velocity is more, we have more interfacial shear stress. Okay, and we have tau I from combined momentum equation already, and we look at the solution. Look at this one. Sometimes it have a minimum point. Okay, let's take a look at the left side of the minimum point. This part, the left side. So this tells me if I want annular flow and make the film thickness to be thinner and thinner and thinner, I need more tau I or more gas flow. So if I flow gas a lot, based on combined momentum equation, if I flow gas a lot, the film becomes thinner and thinner and thinner and thinner. Does that make sense? I think so. If you flow 100% gas, you don't have any film, right? If it is 100% gas, you have no film. If you add more liquid, film becomes thicker and thicker and thicker. Of course. Look at another side. Look at this part of the graph, the right hand side of the graph. It tells me that, hey, if I want thicker film, I should have more tau I. So more gas flow give me thicker film, or if I want thicker film, I have more tau I. Does that make sense?
No.
Oh, okay. Both of them come from combined momentum equation. The difference is the left side is where the film moves up. Okay? The right hand side is where the film moves down. Okay? Your combined momentum equation doesn't tell anything about the sign, right? So when you plot the solution, one part of the graph, left part of the graph, is for the case where the film moves up. Right side, the right side of the minimum point has downward flow of the film. So this part has film move down. Notice that if your VSL is high, you don't have minimum, right? You don't have minimum point. So when your VSL is low, left side is film moving up. Bunny say, okay, film moving up means stable. Okay, stable angular flow. If film moving down, that is not stable, stable angular flow for her. Okay, so how do we separate between moving up and moving down? So we know that left side of the minimum point is moving up, right side is moving down. So if I can find the equation for the minimum point, then I get the transition boundary. So what they do is, you see the combined momentum equation in the form of tau I, that thing, take the derivative. Take the derivative with respect to delta L tilde. Once we take the derivative, make it equal to 0. Okay, what's the question?
So, for example, tau I equal 0.7. Okay, you could have both liquid film going down and going up, right?
It's not like that. When we know for sure that when we have minimum point, the right side, film moving down, it's not stable. They didn't say anything about this case. Because what? Because it's not annular flow to begin with.
I'm
and
sorry,
0.07.
0.07. 0.07, you're gonna have
Where's
2
0.07?
points.
0.07. This part?
Yes.
How I put 0.07?
Yes. So it's gonna cross 2 points. Okay. So it
Oh, when we take a look, we have to look at the solution from combined momentum equation. The solid line is the solution from the combined momentum equation. Look at the solid line. Look at the solid line only for now. The solid line is the solution from combined momentum equation. And by looking at that, they show us that left hand side the film moving up, just that. That's the message for now. The dashed line, we will talk about it soon. Okay? So, alright. To know the left side and the right side, to know the minimum point, the slope at that point is 0. So they take the derivative with respect to delta and equate it to 0. Solve equation, then we get that function. Okay? So to find the location of the minimum, we take the derivative, make it equal to 0. So you do the math yourself. And I do not know whether you do or you did not do or you can do or you cannot do. How do I know that? I test you. Okay? So in this class, it is your responsibility to do this. What is my responsibility? To ensure that you did that, or at least you know how to do that. Okay? That's what I will do. So of course, this kind of thing should appear in the test. Right? So you should be able to take the derivative. If you can do it, okay, it's okay. But if you cannot do it, it's not okay. If you can do it, it doesn't mean, oh, great, you should get it. No, it's not about that, right? The derivative, come on. Okay, we can find that line, right? Now take a look at the dashed line. Tau I, this thing gives us a solid line. Solid line from combined momentum equation is the required interfacial shear stress to make that kind of film thickness. Okay. Now let's take a look at this equation. 5.20. 5.20 is the dashed line. So this is the supply shear stress. Okay, so this is the supply shear stress based on Vg or gas velocity. So if we have gas velocity, so supply line and the required line, when it cross each other, like that point, so that is the solution for shear stress for that particular VSL and VSG. Okay, you see this dashed line, VSG equal to 6. Let's take a look at VSG equal to 25. So if we plot VSG equal to 25, that is our supply shear stress. Okay. What about our required shear stress? So required shear stress, I plot it when VSL equal to 0.1. So this graph tells me that this is not for every cases, it's just for air and water at STP. If it's something else, you cannot use this graph. This is not dimensionless, not universal yet. So this graph tells me that, okay, for air and water and that particular pipe diameter, if I have VSG equal to 25 and VSL equal to 0.1, my fin thickness is going to be that much. Okay, so the cross point between the required shear stress and the supply shear stress is the solution. Okay. Alright, what about this line, this vertical line? This vertical line is not this one, okay? That one is this part. Okay. Let's move on to that vertical line. So taking the derivative, we get that, right? Taking the derivative of that long thing, then we get that. So simple derivative, you should be able to do that. Maybe better, if you don't have any confidence, bring your integration table on derivative table in exam 4. If you need one, bring it. Okay, because it's open book, right? Okay. Early on, we use HLT dot equal to 0.35, right? So this time, Bunny come up with some kind of another reason, okay, some kind of rationale. They say, okay, for simple cubic packing, 52.3%, okay, that is the maximum packing size for the bubble. Okay, so based on that, maximum hole up possible is 0.48. Okay, if we pack more than that, we don't have dispersed flow or something, right? So this is kind of packing criteria. Let's think about the slug body. In the slug body, how much should be the void fraction in the slug body? So the void fraction should be at most 52%. Should not be more than that. So let's say you want to do a quick estimation for the liquid hold up in the slug body. You don't want to assume the value that is less than 0.48. It's not possible, okay? So for that is maximum packing of the drop bubble already. So at least inside the slug body, at the minimum, HRLS should be 0.48. Okay? Early on they use kind of 0.7 something, right? With 0.7 you get HRT equal to 0.35. So this time, use the same approach. If you don't get this, come to me after class, but it is the same approach. Put it in, then we can calculate and get the hole up for the transition. So it's based on the same idea that, okay, if we have the fluctuation in the film, let's say we have the fluctuation, and if the liquid height is more than a certain thickness, then we cannot have annular flow, right? So it's like HL2 equal to 0.35, but this time we have kind of better reason for it. So it's not 0.35. This time it's 0.48. Okay. So HL2 minimum is 0.48. Put it in. Use the same approach. We get 0.24. So this means there's a certain thickness that if we go beyond which we cannot have stable annular flow. That thickness, when we calculate hole up based on that film model, we get 0.065. So this vertical line is 0.065. If we are over here, it's not annular flow. If we are at the right side of the minimum point, it's not annular flow. The film flow backward and we don't have stable annular flow. So this means only this part is annular flow. Okay, and this is a unified model. Okay, combine transition J for everything. So it's valid for horizontal and all the way to upward. Okay, upward flow is a transition J, unified transition J. Now we are going to make it a dimensionless plot. Okay, so this I already explained, right? Slab flow and only that part is annular flow. This kind of graph you cannot really use it, okay, because it is only for water. You are not going to have just water, right? Or it's only for air and atmospheric condition. If you have air at 20 psi, 30 psi, it will deviate. If we use at 200 psi, it's not valid because density is not the same, viscosity is not the same, right? So we need a dimensionless graph. Before we do that, let's take a look on how this graph behaves for different angles. That's 90 degree, 30 degree, and 0 degree minus 90. What you see is that the minimum point kind of disappear, right? Once we have 0, we don't have any minimum point. You see this. We don't have that part of the graph anymore. This is doing this. So the minimum point tells us that it's naturally unstable because the film flow backward. We don't have enough supply shear stress. It is annular flow, but the math tells us that it will flow backward and it's not stable. So that criteria, this kind of thing that we do the derivative, is not for horizontal flow. Okay? It's not because we don't have that anymore. But we can still have that line, right? That line of what? Delta Q of 0.065. We can still have it. 0.065, 0.065. So we can still have it. Okay, but when it's naturally unstable, we don't have that situation. So for transition B that you have earlier, it still works because it's equivalent to that thing. Okay, instead of so transition B is 3.5, right? This is 2.4, and this is newer. So this is both are correct, I think. It will make some difference, but in the log plot, you may not see that clearly. So when you plot VSR, VSG, it's on a log scale, right? It may not make much of a difference, but I think this is kind of more conservative and have more background into it. But it's the same idea.
So this is that there is no annular flow for horizontal or what?
You have annular flow for horizontal. If you have horizontal flow, you can have annular flow. But you use this. Oh, this thing is about unstable, or there are two methods to make annular flow to be unstable. The first way is to have it naturally flowing back. That happens in vertical flow, but horizontal flow it cannot naturally flowing back, right? So that mechanism doesn't happen. So that is not the mechanism that makes annular flow to be unstable. The mechanism that makes annular flow to be unstable is a wave. wave growing mechanism, which is this kind of thing, similar to transition B in chapter 3. Okay. All right. You see 5.19, 5.20. Yeah, where's the page number for that?
It's
201. So 5.19 is the supply tau I, right? 5.19 is required tau I. 5.20 is the supply tau I. The cross point between 19 and 20, or this and that, is a solution, right? It's a solution for annular flow. So the simultaneous solution of 5.19 and 5.20, 5.19 is combined momentum equation, this is the required shear stress. 5.20 is the supply shear stress. We get the simultaneous solution of those equations and make it in a dimensionless form. When it is in a dimensionless form, it is like that. Okay. We don't have. I missed one equation actually. All right. Okay, look at this equation. This equation is a simultaneous solution that we have a graph. We have this not that correct. Let's take a look at the book. Okay. Once we make everything dimensionless, we plot the graph, we get this graph, right? A and B. Okay. Look at this A. Okay. Curve A, stable annular flow, while the condition above of the curve are unstable flow and the transition to slab flow. So curve A is from 5.28 and 5.29. Okay, 5.28 to 5.29. Curve A represents the transition mechanism moving to the instability. It is obtained by simultaneous solution from 5.28, 5.29. 5.28 is this one. So 5.28 is the dimensionless form of the combined momentum equation. That's 5.28. Is it? Okay. So 5.29. So that is the minimum of tau I, right? So when we take the derivative and get the minimum point, that is dimensional form. When we make that equation to dimensionless, it is this equation. So this is the dimensionless form after the derivative. Okay, 5.29. So 5.28 is the dimensionless form of the combined momentum equation. Dimensionless form of combined momentum equation. If we solve this equation and this equation together, okay, we get this line. Simultaneous solution from those two equations give us this line. So which tells us that, okay, this part is not annular. The rest is annular, but this is based on the naturally unstable when the film fall back. Okay. If we solve the combined momentum equation, this combined momentum equation, right, substitute for HL tilde whole up equal to 0.24. Substitute that 0.24 into equation 5.28, which is the dimensionless form of combined momentum equation, we get this line. Once we get those lines, so this is the wave growth formula, right? HL equal to 0.24. Wave growth condition. and that's what is naturally forming for the film flow backward. So this is X and Y. 0 means horizontal. This part is upward flow, downward flow. So this is for unified transition J. This part of the graph is annular flow. This part of the graph is not annular. Okay. If you use this graph directly, you can tell whether it's annular flow or not. Okay. Yeah, let's meet later if you can. Okay, that's it. See you next time. And next time is on Monday. So we have class next time just Monday, Thanksgiving, and then another Monday. And Wednesday after Thanksgiving is exam 4. Okay? Bye bye.